And this is always going to be indicated by a capital P, okay? So to recap, probability distributions and expected value. We're discussing random variables right now. We say a random variable is a function that assigns a real number to each outcome of an experiment. We're going to use similar notation to what we used in Chapter 2 and Chapter 3. F of x here is a variable function expression. We read it as function of x. Here's an example. F of x equals 3x squared plus 4x. So in this chapter, we're going to use capital P of x. That's the probability function of x. And what we're going to be looking at is things like this. This right here is a probability distribution. Why is that? That's not completely centered on the page, is it? Excuse me for a second. So this table right here is going to represent a probability distribution. And x is going to represent the event, and P of x is going to represent the probability of that event occurring. Okay? Not yet. You mean like...
How are they getting the 0 and the P of x?
I have no idea.
Oh.
We haven't discussed that yet. This is just a probability distribution. It's just one that we picked out of the book at random. X represents the event, and P of x is going to represent the probability that the event occurs. Okay? Now, when we look at this, for example, let's say that I say, find P of 2. Well, since I'm considering that particular probability distribution, this is my x. X is equal to 2, so I find 2 in the first row, and then I drop down to its corresponding probability of 0.27. So the probability of 2 in this case is going to be 0.27. We're going to look for 2 in the x row, and then find the corresponding P of x. Now, actually, let me change this just a bit. If you look carefully at that probability distribution table, it maps perfectly to this set of ordered pairs. So it's just like a regular function that we've used before. And I could map these on a Cartesian plane if I wanted to. Okay. Notice, though, that they're both positive values. You will always have positive x's and positive y's. Okay. Probability can't be negative, and the event can't be negative. It's always a positive outcome. Oh, I see what you're saying. So what you're saying then, Jesse, is that gambling is always a negative outcome?
No. It's just funny because it's not just because you find the probability of something doesn't mean the probability is right whenever you.
Oh, I see what you're saying. Okay.
You could lose.
Okay.
But
Okay.
it's positive.
I got it. Yeah, sometimes I'm a little slow. Yeah, your events can never be negative and the probabilities can never be negative. They will always be positive. Okay? And a probability function, as I said just a moment ago, because we were talking about the set of ordered pairs, but a probability function can always be graphed. And that's going to be similar to any variable function. One of the ways that we're going to discuss graphing these things are to use bar graphs. This is actually called a histogram, but let's explore some things here, okay? And let's look at this one on the left, okay? Notice that in this case, the numbers in the probability distribution table, the x's represented hours. I don't even remember what the experiment was, and it really is immaterial for this. But notice that the x values are written across the x-axis in the first quadrant of a graph, okay? And these are actually going to be the midpoints of your bars, okay? And notice that for this first one, we had 0, and I believe the probability for 0 was 0.13. We'll go back up, and in fact, I know what I'm going to do. Oh, I don't need to copy it. It's right there. Because apparently I had that brilliant idea before. Okay. So notice that 0 corresponds to 0.13, and that's right here. Okay? And then 1 corresponds to 0.19, 2 corresponds to 0.27, 3 corresponds to 0.16, 4 corresponds to 0.10, 5 is 0.13, and 6 is 0.02. Okay? And I could draw what we call a frequency polygon by, in fact, let me use different colored line here. This is a frequency polygon by connecting the dots. It's also called a broken line graph. But in order for a frequency polygon to work, you have to come to the left of your first bar and to the right of your last bar. But that's what it looks like. Okay? And basically what this is this right here represents the event and its probability. Okay? So real quick, what's the greatest probability from this particular distribution? Okay, so P of 2 equals 0.27. And then what's the smallest or least probability? Yeah, the probability of 6 is equal to 0.02. Okay? Now, let's consider this table. Yeah.
So we're not actually going to use equations?
We are.
Okay.
We haven't gotten that far yet.
Just doing
Yeah, we're doing the easy part. And the equation's really not going to be that difficult. They're really not.
the same as calculus,
No, it's not going to be quite like that. It's going to be similar, but not. It's not going to be as complex. It really isn't. For example, if x is the event and p of x represents the probability of the event, then what is P of 3? Okay. What is the probability of 3 or 5?
So then you would add them together.
For this one, I'm going to go ahead and say that's going to be 0.16 plus 0.13, which is going to be equal to 0.29. Now, let's further explore this. Somebody tell me what the probability that x is greater than or equal to 2 is going to be.
Greater than or
Right.
so you would do 0.27 plus 0.19 plus 0.13, right? Oh no, greater than or equal.
It's okay.
You're right.
So the probability that the event x is greater than or equal to 2 is going to be the sum of all the probabilities from 2 to 6. Okay? Now, all right, quick definition here. Can't believe I didn't leave that there. All right, a probability distribution called P of x will contain one or more events and each event will have a probability of 0 less than or equal to P of x less than or equal to 1. In other words, the probability of the event can be no less than 0 and no greater than 1. It must be between 0 and 1 inclusive. And the sum of all the probabilities in that distribution must be equal to 1. Okay?
The sum of the probabilities.
Yeah,
Is that what it is?
yeah. Is that better? Sorry. So before we move on, verify that that's a probability distribution. Man, why are you not working? Shit. Bizarre. So we're going to verify that this is a probability distribution. And how would you do that? Yep. Make sure that they're all between 0 and 1. And if they are, good. Now add them all together and make sure that they equal 1.
So you can't have whole numbers?
You could have a whole number, either 0 or 1.
Well, no, but I'm saying like it could never be, like in the x, it could, or in the p of x, it could never be 0 and 1 and 2 and 13.
No.
It could never be.
It has to be between 0 and 1. If a probability is equal to 0, what do you know about that event?
Or no, it's false.
Yeah, it doesn't occur. If the probability of an event is equal to 1, what do you know about the event?
It's true.
It must occur, yes. So, do those 7 numbers add up to 1?
Do they have to add up to 1 or less?
Yes, up to 1. .9? All right, I'm pretty sure I got one, Jesse. Why do you guys always verify what you get on your calculator?
I got 1.1.
Jesse definitely needs to verify because she's all over the place. She's not going to give up her iPhone. So you're a fanboy, huh? All Apple all the time? Yeah. Okay.
No viruses.
Full?
Whatever. Oh my god.
Really? Do you want me to show how nasty a virus I can infect your Apple products with? Because I can. I'm sorry? They do. They do get viruses. Not as many, simply because up until the last 10 years, it didn't matter because Apple products were not the mainstream. But if you think you can't get a virus on your Apple product, you are sorely mistaken.
I know that people can hack into your Apple product.
Oh, yeah. Actually, quite easily. Very easy to jailbreak an iPad.
It's sad because all you have to know is a person's Apple ID, and then you have their.
You don't even need that, trust me.
Oh, okay. Well, but you're gonna smile like the evil.
All right. Checkpoint number 1. We're going to give the probability distribution for the number of heads showing when 3 coins are tossed. B, we're going to draw a histogram for the distribution in part A, and we're going to find the probability that no more than 1 coin comes up heads. And we can do this in the next 15 minutes.
I'm not gonna ask.
Ask questions. What? Go ahead.
Do we need to take into consideration part B before we do part A?
Nope. We do part A first, then we do part B. You can't do part B unless you know part A.
Well, I know, but it says find the probability that no more than 1 coin comes up. That would affect part A.
No, it doesn't. No, it doesn't. Part A is just tell me what the probability distribution is. And the easiest way to do that is to figure out all the possible combinations that exist. If I'm flipping 3 coins, I flip the first coin, it comes up ahead. I flip the second coin, it comes up a tail. I flip the third coin, it comes up ahead. That's HTH. That's one possibility, right? And if we use a tree diagram, so we toss 3 coins, and obviously they're going to be the same kind of coin and they're going to be fair coins, right? So we toss 3 coins, and we use a tree diagram to start, and this is going to be the first coin. And it's either going to be a head or a tail. And then there's going to be the second coin. And let me move this down a little. And I toss the second coin, and it's either going to be a head or a tail, but I have to take into account what the first coin was. So I list the tree branches off of both of the first possibilities. Now I'm going to toss the third coin. And I'm going to list the possibilities coming off of each branch. Now that I've done this, I can go ahead and write down all the possible combinations. This is going to be head, 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 tail.
So you're only tossing each one?
Yeah, that's it. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And then tail, tail, tail. Now, I could have been able to figure out before I did this how many different variations there's going to be, because I take the fact that there's 3 coins and we use this formula, 2 to the n, where n is the number of coins. That would be 2 to the third, which is 8 combinations, or I should say 8 possibilities. And do I have 8 possibilities listed there? Yes, I do. Now, let's go ahead and understand what's happening here. To make the probability distribution, this is the number of heads showing. So that's what we're keying on. That's my event. So H is the event. And we can call it X if we want to, but I'm still going to leave it as H. Which means that the probability of the event is going to be what? P of H. Okay? Now, if I look very carefully at this thing, there are 4 possibilities for heads in these groupings, right? I can either get no heads. How many of them exist where there are no heads showing?
There's 12
Oh, okay. No. Each group of 3 is one event. Okay? All right. In how many of these possibilities are there no heads showing? Just one. That's the tail, 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 right? Okay. So there is one event, or I should say one occurrence, which means that the probability of H being equal to 0 is going to be 1 out of 8, right? Does that make sense? So over here, in my table, I can write 0 and 1/8.
Oh, this is where the decimals are.
Exactly. They didn't use fractions, they used decimals. We can do either one. Okay, I'm going to use fractions here. Okay. So what about where H is equal to, tell you what, let's do this. Once again. So now we're going to do h is equal to 1. Okay? How many of those exist? There are 3 of them, right? So there are 3 possibilities. So the probability that h is equal to 1 is going to be 3 out of 8. Okay?
So you just do this one.
I do. So the next one is going to be h equals 2. How many of them have 2 heads showing? 1, 2, 3. It is exactly the same number. So for 2 heads showing, the probability is 3 out of 8. And then the last possibility is going to be that there are 3 heads showing, which obviously there's only 1 left, right? So that's going to be 1 out of 8.
So now
We will. Okay. But before we do that, we need to verify, is this an actual probability distribution? How do I verify that? Okay. Every probability has to be between 0 and 1. Is that true? Does the sum of 1/8, 3/8, 3/8, and 1/8 add up to 1? Yes, it does. Okay. Yes.
I don't know. Stop at 3. Is that because we're put 3%?
Yeah, there's no way you could have 4 heads, right? What would the probability of 4 heads be? 0. Probability of 5 heads, 0. So yeah, if it's a 0 probability and it occurs outside the normal range of what my events are, yeah, you don't have to list it. But it wouldn't be wrong to list it because you can state unequivocally that the probability is 0 because it can never happen. It's a good question, though. All right, is this an actual probability distribution? So yes. And the reason being, actually let's get rid of that first. Remember the first test is, as I said, is each probability between 0 and 1 inclusive. And that would be a true statement. Number 2, the sum of the probabilities must be equal to 1. Is that true? Yes, it is. Okay, now, it says, and before I do that, let's go ahead and say, look, the probability that h is greater than or equal to 0 is going to be equal to 1. Why? Well, because I would take the probabilities, probability of 0 plus the probability of 1, plus the probability of 2, plus the probability of 3, and I would add them together. So I have 1/8 plus 3/8 plus 3/8 plus 1/8, which is equal to 8/8, which is in fact 1. So therefore, I've just shown visually, yes, it is a probability distribution. So let's talk about drawing the histogram. The histogram is going to be actually fairly simple to draw. Go ahead and set up a first quadrant on your paper, or whatever you're doing. And then you're going to take each probability and list it. There's going to be the 0. There's the 1. There's the 2, and there's the 3. And those are going to be your midpoints of your bars that you're going to draw, okay? And since I only have 4 possibilities for probabilities, I can list those on the vertical axis, and that's what I'm going to do. We'll list 1/8, 3/8. Actually, you know what we're going to do? We're going to go ahead and list 2/8, and then we'll list 3/8, and then we'll list 4/8. And I know what you're saying. Why do I have to do that? Well, I want to make sure that we have an accurate scale, okay? So for the first one, the probability of 0, that is 1/8. So I draw my bar, where 0 is splitting the bar in half. And that's going to yield a point up here. And it's at 0, 1/8. Then I'm going to draw my next bar for the probability of 1, and that's going to go up to 3/8. Now notice that the bars are touching, and they have to in order for it to be a histogram. You cannot leave any separation between the two. That's okay. Then the next one is also at 3/8. I don't necessarily have to draw both of these lines here, because if I did it on a computer, there would be no actual delineation. And I forgot to put a point here and a point here, because I can actually draw the frequency polygon from that. And then the last one is going to go up to 1/8, just like the first one, and there we go. That is my frequency distribution histogram. Now remember, this right here is your probability. And this down here is your event. And it's the number of heads showing. But I haven't completed the problem yet, have I? Because I need to find out what the probability that no more than one head is showing. Is that what it says? Yeah. So, find the probability and what that comes out to be is the probability that heads is less than or equal to 1, right? Or you could write it as the probability of no heads plus the probability of one head, which is really what you're going to do, okay? And so that's going to be equal to, actually, let me change this just a tad, and then we'll rewrite what I just said. So we could write this as the probability that h is equal to 0 or h is equal to 1, which is the same thing as the probability of 0 plus the probability of 1. And I could write it as h equals 0 and h equals 1 if I want to, but that's really going to boil down to 1/8 plus 3/8, which is equal to 4/8, which is equal to 1/2. And if you want to go ahead and write it as a decimal, you go right ahead. 0.5. Okay? We're done.